register banks, the bit addressable memory, and then some general purpose memory. And then above that 128 bytes, you've got another 128 bytes which contain special function registers. Some of those are bit addressable, and some examples of those special function registers are the ports. And ports are bit addressable. So, very sort of trivial example here, set B P13 is just simply making that particular pin on that port go high. This is, if you like, one of the more powerful features of the 8051. General purpose microprocessors tend not to have the ability to manipulate individual bits like this. If that was the case, what you could do is you could take the value of a whole kind of port, if you like, load it into the accumulator, make an adjustment, and then write the whole thing back. With the 8051, you can manipulate individual port bits straight away without having to first move it into the accumulator to manipulate. Okay, and then there's a little example here, not a very exciting one, of some kind of strange washing machine where we're going to fill it with water, and then when it fills up, we're just going to rotate the drum left and right, or clockwise and anti-clockwise, forever. So it's a very strange washing machine. You never get your washing back out, but there we go. So they're using two pins here. One of them, which is a test, pin 1, 2, is indicating when the washing machine's become full of water. And in fact, that's the only bit we're testing on. So when the washing machine fills with water, until that point in time, so if no bit's set, we just keep on waiting here. So when pin 1, 2 is low, we're just stuck in that little loop forever here. But when this becomes high, i.e. when the washing machine is filled with water in this case, this test will fail because the bit's not set. It is set now. We'll move into here, and at this point in time, effectively, we're turning on the washing machine motor, apparently, which will get it to start going in one direction. It's not clear which, it doesn't specify which direction it's going to rotate in first of all in this particular program. So it's just going to start rotating in one of the directions. The direction is actually controlled by P24 in this, but we haven't initialized it to any value. So it's just going to start rotating in one direction when we switch it on. We then come into here, and we've got a little subroutine that's not shown in this program. So we would be jumping to somewhere else and counting down some register. When we've done that for a little bit of time, we would come back here, or if you like the instructions straight after it, and then we would toggle this bit here. Complement is just inverting that bit, this is the rotation direction bit, which will cause the thing to start rotating in the opposite direction, and then we just go back to here, and then wait again. So this is just going to rotate one way for a while, then it's going to rotate the other way for a while, and just keep doing this forever and ever. Not a very sensible program, but it's just showing you some bit manipulation. So in addition to the ports themselves, there are a number of special function registers which are bit addressable. Some of them you've already met, and some of them we haven't done yet. We're doing more of them. The program status word, remember you're supposed to know all the details of that one. Interrupt priority and interrupt enable, we might do those this morning. See how far we get. Generally speaking, it's better to write accumulator as A, by the way. But ACK, the accumulator. SCON is the serial control register. We haven't done that yet. We're going to do that definitely this morning. Sorry, we're not going to do that one this morning. Correction. We're going to do that in about a week or so's time. TCON we're definitely going to do this morning. That's the timer control register. That's a bit useful. Okay, anything I want to say about that? Okay, there's some more here. We've kind of done this before, really, so this is just reminding you that for those registers which are bit addressable, you have multiple ways of writing to them. So for example, port 0, it has a byte address, and it also has these bit addresses. Okay? So, for example, if you set move into the accumulator immediately, I don't know, 07 hex, move into port 1, the contents of the accumulator. That would write a whole byte to this. You could achieve exactly the same thing by saying move to 80 hex, the contents of the accumulator. Okay? That's just the direct address for port 1. If you were to do something like set B 80 hex, that would actually go in and just make that individual bit in port 0 go high. Okay. So for those of you with remarkably good eyesight, you might just be able to read this. This is showing you all the special function registers, I think. Yes, because below 7F and below is all the low 128 bytes of internal data memory. So starting from hex location 80 upwards is the upper 128 bytes of internal data memory in the 8051. And you've seen this slide before, or this bit of it before. This is showing you, over here is the names of the special function registers. And if you see a number in here, that's the bit address of that particular bit in that register if you wanted to manipulate that individual bit. Yeah.
If you wrote a whole byte to a bit, does it wrap from the middle of the
I would think if you try to write a whole byte to a bit, the assembler would actually stop and not let you do it.
So it wouldn't start from that location and wrap around to the next address?
If you, I'm trying to think of an example where you could do it.
So the assembler will know that, like, 9D is actually a byte location and not.
It's usually based on the instruction itself. It knows, depending on what instruction you're invoking. For example, set B, it's obvious it has to be a bit address.
But say you did like a move the accumulator to 9D, would it start from there?
If you did a move the accumulator to 9D, I think it would naturally assume you're moving a byte. There is a special move instruction, move C, which is actually move the carry flag to somewhere. And the carry flag can be used as like a 1-bit accumulator. Now, if you did a move C to and then a direct memory address, because it knows the carry is a 1-bit entity, I think it would just move to the bit address, direct address. So again, it's implicit in the instruction.
So if you tried doing a whole byte, it wouldn't work.
Well, if you did say move from the accumulator and then gave a direct address, it's going to move a whole byte from the accumulator to the direct address, because that's what it will infer.
Yeah, starting from that address. So in the middle of a byte would be the beginning of your data.
Oh, when you're writing a whole byte, the least significant bit of the accumulator becomes the least significant bit that's written in, and so on. Am I not answering your question? Yeah, if you loaded a whole byte of information into the accumulator, yeah. An accumulator is an 8-bit entity, and then you did move the contents of the accumulator, and you specified an address. Let's say you specify the address A0. Because you're using the instruction move the contents of the accumulator to A0, it will just infer you're moving the whole byte of the accumulator. And the least significant bit of the accumulator will be here, and so on.
So if you did instead A4, would the least significant bit start at A4 and wrap round to
No, no. If you said move the contents of the accumulator to A4, it will actually try and write it to byte address A4,
right.
Which is actually, A4 is not defined. So who knows what would actually happen?
So it wouldn't start in the middle? Or
no.
Right, okay.
If you want to do it to start in the middle, you'd have to do a series of those rotates,
right.
Manipulate the accumulator, and then write it. No, it's not going to do that. But if, for example, like I say, I had something in a carry flag, and I did move the contents of the carry flag to somewhere, and then I gave an address such as A0, that would actually go to that individual bit, because it's implicit in the instruction that we're dealing with 1-bit quantities. But no, what you're saying, no, that kind of thing doesn't happen. So, not all of the memory locations from 80 to FF are actually occupied anyway. And if you try to write to those, basically Intel say, I'm not going to guarantee what's going to happen anyway. There may not even be any memory there anyway. But for those places where there are special function registers, you can see which ones you can manipulate individual bits and which ones you can't. Anything that's... This slide is just reminding you to be careful that depending on the kind of instruction you're using, that if you like, certain parts of memory, they have two addresses associated with them. They have the byte address, and this is sort of showing you, for example, in the internal data memory, byte address 2F, you could actually also be writing to these individual bits. So the same locations effectively have two addresses associated with them. That's all it's saying. So if you wrote set B 2F, clearly it's not going to write a whole byte to here. It will look for bit address 2B, which would be somewhere else in the bit addressable memory, and just change that 1 bit. I've kind of hinted at this already. The carry flag is used not just for basically arithmetic operations, for working if you've got big numbers and things like that. It actually functions as a 1-bit accumulator. And that's one of the reasons why there are so many, if you like, conditional jumps based on the carry flag. So you could load an individual bit into the carry flag, do some tests on it. So and there's some code here. Basically, we're being asked to write a little bit of program code here. So it's going to be some, if you like, answer phone. And what we've got, bit address 12 hex is going to be a flag. And depending on the state of that flag, we're going to either display the message, there are no messages, or there are new messages. So, again, a rather contrived program. So first of all, we're moving the contents of that bit memory location, and we know it's a bit memory location because it's implicit in the move C. Because, if you like, the processor knows that C is a 1-bit entity, so it's not going to try and move the whole contents of byte location 12 in the internal data memory. It will go to bit memory location 12, which will be somewhere in that in the range 20 to 2F. You know what I mean? And it will fetch memory location 12, the contents of that, and put it into the accumulator. And then we're doing a test on the not accumulator, on the carry flag. We're doing a test if no carry not set, if you like. So if it's not set, we jump to no. Otherwise, we do this bit of code here. So if it is set, we would basically, what we've got here is somewhere we've written into the internal code, well, into the code memory, some kind of information like a message. And this is, we're using data pointers as a pointer to that internal code memory where this message begins. What we've done before is org 400, I think, was it? Org 400 hex. We would have written define byte, and then we would have written some kind of message, which would start from memory location 400 and go up a series of bytes, which would be ASCII characters for the message. So, given that the flag isn't set, we're going to write out the message for whichever message is appropriate for when the memory location 12 has it's clear, which is, I think, no messages. So at location 400 onwards in the code memory is an ASCII string that says no messages or thereabouts. So we're just pointing the data pointer at it, and then we're calling a routine to actually display those ASCII characters. And And then we're just jumping down here to exit, and that's the end of that. Oh, in fact, I didn't see we got it all here. So there, in fact, this is, so location 400, that's the ASCII string, no messages. And then we've got here at 420 hex onwards in terms of the code memory, we've got another string, no new messages. It is up to you, the programmer, to make sure that when you choose these orgs, this is far enough away from that one that when you write this one, it doesn't overwrite the earlier message when you're actually programming the device. Okay? If it is set, sorry, if it was set, no carry, so no. So if it was not set, we would go into here, and if it is set, we would do this thing. So if it is set, we're doing this message, new messages, and if it's not set, we skip over that, and we do this message, no new messages, and that's it. Radically exciting there. I have been asked a number of times, in an exam, are you expected to write in the assembly language? The answer to that question is yes, you might. And in past exam papers, you have been expected to be able to write little bits of assembly language. The good news is all the instruction set is there for you. Okay? Generally speaking, though, more often than not, you'll be given a piece of assembly language and you're asked to interpret it, to explain what's going on. I'll say something more about the exam. There are 6 questions. They're all multi-part essay questions. And 3 of them will be focused on the first half of this course, and 3 of the questions will be focused on the second half of the course. And by the first half of the course, I mean primarily about the architecture of the 8051, like how is it organized, that kind of stuff, and also about the assembly language. So you can probably expect in an exam to come across 2 essay questions which are almost devoted completely to assembly language. Now, if you hate assembly language, you really want to avoid it, you can rest assured that half of this course is to do with interfacing, which we're going to be doing in about 2 weeks' time. There's going to be 3 exam questions which are devoted to the kind of interfacing side of the 8051. Okay. Another thing to bear in mind this year is we're being told by registry, I think I've mentioned this before, to mark the first 4 questions that you attempt. Okay, so if you actually answer 5 questions, we're being told not to ignore the 5th question. It's not like we're going to mark all 5 of them and pick the best 4 of the 5, and that's what you get your mark on. We only mark the first 4, which is different from where it used to be, as far as I remember. Okay, so this is this is something I do want to talk about. And I'm going to do a little drawing here. We're actually going to meet this again when we talk about interfacing later on. Oops, don't want to do that. Get there eventually. All the ports on the 8051 are bidirectional, which means that you can write to them and use them as output pins, or you can read from them. And I'm going to show you what a typical port pin looks like. Oops. Without trying to lose all the paperwork. almost done. So for a particular pin, it actually is rather complicated. This is the, if you like, the rest of the internal operations of the 8051, you know, the bus that connects the CPU to the port, so to speak. Okay? So a particular pin, there's a transistor associated with that pin. And if, for example, you wanted, we're using it as an output, and you want the pin to go low, what effectively we want to do, we would switch this transistor on. Switching this transistor on effectively almost connects this down to ground. It pulls the pin low. Okay? And you would achieve that because of the inverter here. So when this, this goes low, sorry, when this goes high, this goes low and this is switched off. When this goes low, this goes high and switches this on, which pulls this low. So when this is low, this goes low. I'll say that again slowly. If we were to write into here, to lock into this latch, the value such that Q is low, that means this inverter will make this thing go high, which will switch this transistor on, which will therefore bring this pin and pull it down to ground. It will basically connect it through here down to ground. And so the pin is low. If you were to make Q go high, then the output of this inverter will go low, which will switch this transistor off, so it's as if this transistor doesn't exist, and the internal pull-up resistor here will pull the pin high. Okay? So that's when we're using this particular pin as an output, that's how we achieve that control. Now, in the case of ports 1, 2, and 3, that's exactly how it is. In the case of port 0, this resistor in certain modes doesn't exist. It's left unconnected, in which case it means you're going to have an external resistor here to pull it up when you've basically switched this transistor off. Otherwise, the pin just floats. Now, if that's kind of I'm going into too much detail there, don't worry, we will be coming back to this anyway. However, the other thing I wanted to show you is we've used this as an output, and we now want to read it. Let me see. Let's say that this pin, I now want to make it behave as an input. And let's say that the last thing I did was to have this, I've got to be careful, have Q low. So I was using it before as an output, and the last thing I wrote out to this pin was that I wanted to be low. Okay? So let's see what that would have done. So Q's gone low, which means this has gone high, which means this transistor is switched on. Which means that effectively you've got a pathway down here. Now let's say, oh yeah, I've changed my mind now, I want it to be an input. And you then decide to connect this pin to VCC. Which, now you might be careful, you might connect to VCC through a resistor, but you might say, I don't want to do that, you can connect it to VCC directly, or there's a very small resistor here. If that was the case, given you've left this transistor switched on, as soon as you do this, there's going to be current that's going to flow through here, through the transistor, and almost certainly burn out the transistor, destroy it. That's bad news. So, if you're using a pin and sometimes you want it to be an output and sometimes you want it to be an input, and you might say, why the heck would I ever want to do that? Well, if you don't want to do it, fine. But there are some occasions where you might want to use a pin, sometimes to drive things to be as an output and other times to function as an input. If that is the case, when you're using it as an output, you must remember that the last thing that you write out is a 1. Make it go high. Because if we make Q go high, this invert will invert that and switch this transistor off. Okay? So you will left that, this will have that kind of locked into it, and this will be switched off. So that then, if you were to connect VCC to here, doesn't matter, it can't go down to ground here. And you can test the status of that pin here. Okay? So the rule with the 8051 is if you're using it always as input, you don't need to worry. If you're using it always as output, you don't need to worry. If you're going to use a pin as outputs and inputs, you have to have the discipline to remember the last thing you write out is make all the pins go high that are going to become inputs. And the purpose of that is to make sure that this transistor, and there's one transistor per pin, this transistor's been switched off. If you don't do that, it may not be a problem, but if you forget and you happen to connect that pin to VCC, then a very large current is going to flow through this transistor and probably destroy it. So it's a kind of programming convention. We tend to, if we're going to use any pins as inputs, whether they've ever been outputs or not, a sloppy programming style is to just write 1s to all the pins on the 8051 before you start using them as inputs. And that way you're absolutely sure everything's safe, because you'll have switched off all of these transistors. So that's the first thing you need to bear in mind. There is actually